All right, so this is our video on ocean acidification, which has been called Climate Change's Evil Twin, and we will talk about a little bit more why that is later on in this video. So first of all, what is ocean acidification? So ocean acidification is the direct chemical change to global ocean chemistry because of the increased levels of carbon dioxide that we are emitting as humans. So it's said that by the end of the century, our oceans could be about 150% more acidic than they are today. And that seems like a huge jump in our pH range, but really, if we're looking at the pH scale, that's only about a half a pH point more acidic than it is right now. So this is a condition that we have not seen on Earth in probably 20 million years, and it's something that the organisms are not quite used to. What is in seawater? So our main component of seawater is obviously water, our nice H2O. The ocean does contain almost every single element that is on the periodic table. And when you dive into the ocean and you get a big gulp of that water in your mouth and you taste salts, most of that is going to be NaCl, which is your table salt. We measure our dissolved salts using something called salinity, and we'll do salinity tests in the ocean, and we'll do salinity tests in just local rivers, streams, ponds, everywhere else as well. Some other chemicals or components that we might find in seawater are things like magnesium, sulfate, and calcium. So why is this so important? Well, if we have an increased salinity, then we can actually dissolve less gases in the seawater. This is the same correlation with temperature. So if the temperature increases or the salinity increases, the amount of gas that we can absorb in our seawater is going to decrease. So let's talk about pH for a second. pH is going to be a measure of your hydrogen concentration in a solution. So we're going to measure the acidity or alkalinity of a solution. Remember that when we're talking about alkalinity is really just another big fancy word for a base. pH is only talking about H plus ions, okay? When we're talking about bases, we're going to be talking about OH negative ions or hydroxide ions. pH is a logarithmic scale from 0 to 14. So remember that 0 is acidic, 7 is neutral, and 14 is basic. We want to be drinking water around a 7, and our ocean is around an 8.1. And here's what I said earlier. Our 0 end is going to have that nice surplus of hydrogen ions. So you'll see on this graphic that we have the hydrogen ions over here. And then on our basic scale closer to 14, we're going to have the hydroxide ions or the OH negatives. When we're measuring the OH negative ions, we're going to be doing something called pOH in the substance. So that's just kind of flipping the scale and looking at it from a basic side instead of an acidic side. You do need to know how to calculate pH, and it's not as hard as it looks. You are really taking the negative log of your H plus ions. So, for example, if it's this one, you're taking the negative log of 0.001. And that looks really scary. But all you're really doing to find the pH is you're taking that 0.001 and you're moving the decimal to make it a whole number. So the pH of this one is really just 3. Now to find the pOH, you're going to take 14 and you're going to subtract 3, and that's going to give you your pOH. So the pH is equal to 3, and I got that from just moving my decimal place, and then my pOH, or the hydroxide concentration, is going to be equal to 11. And I got that from subtracting 3 from 14. Now what I want you to do is try your hydroxide concentration. You're going to do it in the exact same way, except we're looking at the OH negative concentration instead, and type your answers into the box. All right, here is our pH scale. So again, 0 is very acidic, basic is 14 or alkaline. Our seawater is about an 8.1, and this is changing. And then here's what I was saying earlier about that logarithmic scale, or small changes in pH will be really great changes in acidity. So if we go from an 8.2 to an 8, that's almost a 50% change in acidity. That's a huge change in acidity for marine organisms. Even this, just a 3 or 0.3 change is a 100% change in acidity. So if we're thinking about ocean acidification over time, if we end up going from this 8.1 to a 7.5, marine organisms are not going to be able to adapt as fast as we have been changing the ocean chemistry. Why is this happening? Well, ultimately, we are talking here about our carbon cycle. So remember that with our carbon cycle, we are mainly concerned with carbon dioxide, which is in our atmosphere. Our atmosphere is a sink for carbon dioxide, so is where we're going to have most of our resident carbon. And carbon is a greenhouse gas. And like I said in class, we do need carbon dioxide, and we do need this greenhouse gas, because without a greenhouse gas like carbon dioxide, the world would be just a frozen ice ball. So we need this greenhouse gas in order for life to function. We also need carbon dioxide because plants go through photosynthesis based on our carbon dioxide. So if we didn't have carbon dioxide, plants would not be able to photosynthesize. And based on that photosynthesis, we get our oxygen. Without oxygen, we wouldn't be able to respire, and then we wouldn't give off this carbon dioxide. So we have this nice little cycle just based on around us and plants. Our oceans are going to have an equal exchange with the atmosphere. About 30% of the carbon dioxide that is in the atmosphere is going to be exchanged with our oceans, and we want to create some sort of equilibrium between the ocean and the atmosphere. So what that means is if we increase the carbon dioxide in the atmosphere, we're also going to increase the carbon dioxide in the ocean, because they want to remain at some sort of equilibrium with one another. Sources of CO2. Well, up until 1850, we were doing fine with CO2, and then we found these awesome things called fossil fuels. And you guys are experts on fossil fuels now. Our coal, oil, and natural gas industries were booming, and we decided that this was a great thing to burn. And remember that combustion will give off your CO2. So whenever we burn our fossil fuels, we are going to release carbon dioxide into our atmosphere. But not only that, during the Industrial Revolution, we were trying to feed more people, because the Industrial Revolution led to a boom in population. So we started to convert land into agricultural fields. And as you read in your case study, the conversion of agricultural fields leads to a carbon loss, or a carbon sink loss. Ultimately, the birth of the Industrial Revolution was also the birth of this idea of ocean acidification and global climate change. Because if we're trying to create this equilibrium between the atmosphere and the ocean, the more CO2 we're pumping up here, the more CO2 is going to be dissolved down here. Just to put it in perspective, over the last 200 years, about 2 trillion tons of CO2 have been released into our atmosphere, and about 550 billion tons are have been absorbed by the oceans. All right, so when we're talking about ocean acidification, we are going to be referring to these 3 major chemical reactions. So first, we're going to have carbon dioxide. It's going to react with water, and it's going to form something called carbonic acid over here. This is carbonic acid. Now, carbonic acid has a very, very short time in ocean water. It's actually going to dissociate or break down very easily. So we have our carbonic acid here. It's going to dissociate into our hydrogen ion and then something called bicarbonate. And you probably often bake with bicarbonate because the bicarbonate is just another way to say baking soda. So when we dissociate carbonic acid, it creates a free hydrogen and then bicarbonate. Well, then our bicarbonate is going to dissociate again into another free hydrogen ion and then a carbonate molecule over here. So it looks like from this, ocean acidification is occurring because we have this stuff called carbonic acid forming in the water. But this is not what is causing ocean acidification because it dissociates so quickly. The increased number of hydrogen ions in the water is what is going to cause ocean acidification to happen. All right, so let's talk about the chemistry behind this. So if we're absorbing more carbon dioxide into the seawater, the pH is going to eventually lower. So why does this happen? So our carbonic acid is going to break down or dissociate to create that free hydrogen ion and then bicarbonate. The hydrogen ions are going to lower the pH of the ocean water, but then the ocean is going to try to find an equilibrium by adding carbonate to the hydrogen to create bicarbonate. Now, what the real issue is here is that carbonate is normally the building block for shelled organisms like corals and oysters, and it's going to combine with calcium 2 plus in order to form this stuff called calcium carbonate. So CO3 plus Ca2 plus leads to calcium carbonate. And this is so important for the creation of our marine organisms, our shelled organisms. So if we're taking away this stuff here, we're going to undersaturate the water with carbonate, but we're going to keep the same amount of calcium, and we're just going to decrease the pH, and the ocean is going to try and find some sort of equilibrium and keep using this and keep putting this with our hydrogen in order to form bicarbonate, and nothing is ever going to grow the same way it did before. So consequently, there will be a decrease in sea life because we don't have that calcium carbonate in order to form our seashells anymore. So that's ultimately going to affect the biology. Photosynthetic algae and seagrasses will benefit. Well, that's because they survive on carbon dioxide in order to photosynthesize. However, our calcifying species will obviously suffer because we're taking away that calcium or the carbonate, and they can't create their shells like they did before. Corals and calcifying organisms are going to use that calcium carbonate to create their shells through a process called calcification. So one example of this that we have seen in the recent years is the Great Barrier Reef. The Great Barrier Reef calcification has actually decreased by 14% since the 1990s. And these organisms are the base of our food chain. So if we are not worried about this, then it's going to affect the entire food web, because these little small guys are what are going to feed the bigger guys and eventually feed us. So one of our case study species, and this is a very, very tiny guy, is called the pteropod. And pteropods are basically sea snails. They're nicknamed the sea butterfly because they are free swimming snails, and they're found all around the world. They're also nicknamed the potato chip of the sea because they're a very important food source for many marine organisms. Like the krill and whales and salmon. These are especially important on the West Coast because they're the main source for pink salmon, mackerel, and herring, which is a very important fishery on the West Coast. And the West Coast has actually seen huge effects on these little pteropods, and scientists are seeing effects on them that they were not expecting to see this early in the 21st century. So they're seeing a lot of breakdown in their shells through here, and this is actually a study that they have done, and they said that if our pH drop continues to decrease like it has so far, then by 2100 it will only take 45 days for this little pteropod shell to completely dissolve. Now, what it means right now is ocean acidification is basically preventing this little pteropod from being able to build their shells or fix their shells if it's cracked. So they don't have the energy and they don't have the carbonate in order to create their shells and create protection from other organisms. Our next case study species are shellfish. So shellfish are things like bivalves, like oysters or even scallops. There has been a lot of research on oysters because it is a huge economic point for us. So the oyster industry in the United States brings in about $740 million to $1 billion worth of revenue for us. So we are really concerned about what is happening to our oysters because this is something that is occurring worldwide for them. So they're really looking at the lowering of pH because, again, the low pH will create an undersaturation of something called aragonite, which is just another form of calcium carbonate. But the oysters are going to use that aragonite to build their shells. So if we don't have the aragonite, they can't build their shells. And actually, in acidic waters, oyster larvae won't even try and build shells. They'll just die. But our mature oysters, their shells will thin, their growth will slow, and then the death rate increases. So if we are looking at the Chesapeake Bay here, the Chesapeake Bay has been considered a ocean acidification hotspot for this to happen in the future, ocean acidification to happen in the future, because we already have such problems in the Chesapeake Bay. We have the nutrient pollution of the nitrates from agriculture, and then we have a whole lot of sewage runoff from the number of people that live around the Chesapeake Bay, which adds, again, the added nitrates. And then we actually do not even monitor for ocean acidification in the Chesapeake Bay. So we could be directly impacted by this in Virginia, which is it's a big part of our economy. Luckily with oysters, they do have a lot of genetic variation between oyster species. So there is a lot of research going on right now about if they are able to adapt to the change in the pH of the waters because they already are an organism that is used to dealing with change. All right, our last case study species are coral. And coral are considered to be the rainforest of the sea. Most of our coral are sclerotina coral. So it's like what you would normally, I guess, think of as brain coral. Sclerotina coral are really hardy stone corals, and they often create colonies. But corals are so important because they can house between 600,000 to 9 million species, and we're not even really quite sure how many species these coral reefs or what kind of species these coral reefs hold. Coral reefs are kind of like the last frontier that we have because we have no idea what's down there. The reason why organisms love these things so much is because of the complexity of the reefs. Look at all of these nooks and crannies for these for organisms to hang out in and hide in. I mean, it's a structural wonderland for organisms. They can hide wherever they want. Corals are going to rely on the saturation of carbonate to build a reef, and then other organisms are going to depend on the corals building their reefs for their habitat. So if we're thinking about ocean acidification, we're going to reduce the coral's ability to build themselves and to build the habitat for other people. And then our loss of calcium carbonate is also going to lead to things like mechanical erosion, bioerosion, which just means another organism is going to come along and eat it like a parrotfish, or bore into it like a worm, and then we'll have the dissolution or the dissociation of the calcium carbonate of coral reefs. So over time, this is going to make it impossible for our coral reefs to recover, to rebuild themselves, to fertilize, and then for new larvae to create a coral reef. So right now we're looking at a erosion rate that is a lot faster than a rebuilding rate. And the sad thing is that it's actually coupled with this issue called coral bleaching. And this is kind of coupling it with that idea of global climate change. So if we're adding more CO2 to the atmosphere, we're increasing the global temperature, and which will eventually increase the temperature of the ocean. So coral bleaching is an issue where we have algae that live inside of the coral. The coral's color actually comes from a mutualistic relationship between coral and something called zoolanthe algae. So the coral is not actually a beautiful color. It's actually the algae that lives within the coral. And the coral rely on this relationship because the algae provide food to the coral. They provide the carbohydrates that the coral needs to live from the algae completing photosynthesis. So when we have coral bleaching occurring, the warmer water actually makes the coral expel the zoolanthe or expel the algae living in the tissues of the coral. Then doing this process is going to turn the coral completely white. So they go from this nice, beautiful color to a very bright white color. And it reduces the coral's ability to fight disease. It reduces the coral's ability to rebuild itself. It doesn't mean it's dead, not yet, but it does increase the coral's mortality rate. So it's a big problem coupled with ocean acidification, because if we're bleaching the coral, if they are not getting the food source that they need from the zoolanthe because they're expelling it because the water temperature is too warm, and then we're also decreasing the amount of calcium carbonate in the water so they can't even build their skeletons, then we are really putting a harm on our coral reef. So this is an example of what it might look like. We have our nice coral reef over here. So we have our zoolanthe living in the tissue of our corals, and then this is what happens after coral bleaching occurs. So it's completely white. We've expelled our zoolanthe into the water, and hopefully over time the water will become cool enough that they will take in their zoolanthe again and they will survive, but it just has to be in the short enough amount of time for that to occur. Coral bleaching can also occur from being way too close to the sun. It can occur from the water being way too cold, and then it can occur from excess pollution as well. So in short, and to wrap things up, slight change in temperature can really harm a marine organism's ability to live. So increasing the amount of carbon dioxide in the air is going to increase more incoming solar radiation because it's a greenhouse gas, which can eventually lead to something called coral bleaching. But as that happens, carbon dioxide is going to dissolve into the ocean, creating carbonic acid, creating free hydrogen ions, which is reducing the amount of carbonate in our water. And that carbonate is what our shelled organisms are going to rely on to create their skeletons. So no carbonate equals no shelled organisms, or less shelled organisms that we have had. So why does this affect you? Well, we have barely discovered what is occurring in our coral reefs. Coral reefs and marine organisms in general, oyster reefs even, protect our shorelines. Coral reefs and oyster reefs support fishing, they support tourism, and it could be the next potential place where we go for a medical breakthrough. So the cure for the common cold could lie right in a coral reef. So economically, medically, recreationally, these places are so incredibly important for us to take care of. So, and I mean, if you like to eat anything really at all, it's something that you need to focus on and we need to take care of as a whole. Here is a great representation of what occurs. You may want to take a snapshot of this just so that you know what's going on, because this does a great job of simplifying the process and showing what's going on. So here's a nice little hydrogen ion here, acidifying the ocean, and here's our coral reefs over here. So I'm so sad. Okay, bye.